We're going to take a look at solving some applications of rational expressions. So we're going to go ahead and start with the easiest, which is going to be the proportions. So let me grab my writing tool here and explain this. So what a proportion is, and you see kind of an outline of it right here. If you have two fractions that are equal to each other, and there's a property of proportions that their cross products are equal to each other. So for example, mathematically, 1/2 we know is equal to 3/6. And the cross products, and by cross product, we're cross numerator with denominator. So 1 times 6 is 6, and then the other cross product would be this direction. 2 times 3 is 6. And so we can see that if they are in fact true proportions, their cross products will be equal. And so this idea of a cross product is really still the common denominators in an equation that we cancel out. So for example, if I just generically write A, B, C, and D as the numerators and denominators of two fractions and set them equal to each other, well then in this particular case, BD is the lowest common denominator. If I multiply both sides by BD, here on the left side, the B here would cancel with the B here, leaving me a D. It'd be D times A. And likewise on the other side, the D would cancel with the D. So this D cancels out and it leaves you C times B. This right here is the cross product, right? D times A and B times C are cross products. And so instead of going through the process of lowest common denominator and canceling denominators, we just know that these will always end up as cross products. Okay, so the way that these get used usefully is going to be in problems such as this, where we can be given a relationship between two entities. Let me go ahead and erase this out here for you. So we're going to be given relationships between two entities, and we will set them up as a fraction or a ratio, and then we'll set it equal to another fraction or ratio, only of which half of it was given to us. So let's look at this example. So here we have you can read the text with me. But in Washington, D.C., the tax on property assessed at $1 million is 220, or excuse me, $22,000. If the rates are proportional, then how much would the tax be on a property assessed at 920,000? So being proportional means that if the price of the property goes up, so does the taxes. And likewise, if it goes down. So the key thing with setting up a proportion is you first have to relate the two things that are connected to each other. So in this particular property, if you took a look at what is connected to what, the 1 million is connected to the 22,000. So I'm going to write that as a fraction. That doesn't matter what the numerator is, what the denominator is. I'll tell you why in a minute. So if I do that, then I'm going to set it equal to, let me drag this down a little bit. So I'm going to set, here's my fraction, 1 million over 22,000. Those two things are related. And then they give me half of a similar relationship. Here they give me the $920,000 property value, and they ask, well, how much tax? What is the tax going to be? So when I set up these two fractions, the only thing that's important about the setup is if I choose to put the value of the property on top, then the value of the property has to be on top in both fractions. The bottom, I elected to do taxes, so both are taxes. The X is what I don't know. It's what I'm trying to compute. Well, this, if you look at it, is a proportion, two fractions that are equal. So I simply do the cross products. So when I multiply 1 million times X, that will be equal to 22,000 times 920,000. And when I'm done, I get a value that X is equal to 20,240. It's real simple on a calculator. Just multiply 22 by 920 thousands and then divide by a million, you got your answer. Okay, the answer, does it make sense? Yeah, sure it does, because Um, the 920,000 is a little bit less than a million. So my taxes I would expect to be a little bit below 22,000, which it is. Okay, let's look at another example real quick. Going to Mexico and you want to change your dollars into pesos. Okay, so let's go ahead and take a look at that. So, what is the relationship we're given in here? We're given that $1 is worth 18.36 pesos. So that would be my one fraction. The one represents dollars, the peso is 1836. All of that will be equal to, and then they gave me $250 that I'm going to turn into pesos. Since I put dollars on top, I have to put the 250 on top. They want to know how many pesos that is. That's the X. And then I simply do the cross products of this proportion, and you'll get 4590. Okay, this next problem would be easy enough to figure out without a proportion, but let's just assume we couldn't do it. Again, the 168 calories is associated with 10 ounces. So there's my first fraction. The 30 is the ounces. Ounces are on the bottom. So I put 30 on the bottom. The calories are on top. That's the X. And then I cross multiply and solve for X. I get 504 calories. Okay, so these are real easy. Uniform motion, a little bit more difficult. Okay. These problems you can, you're going to create a table if you want to. You don't have to. But the key thing that you're going to know with these particular problems is the formula distance is equal to the rate times the time. Now you may have to manipulate this particular equation depending on what you're given. Okay, and so when you read the problem, you are going to go through it and you're basically going to fill out the information. So let's carefully read this problem and make sure that we understand exactly what we've been given and what it is that we have to figure out. Okay, so let me go ahead and erase, just clean this up a little bit. Okay, so um, on a float trip, Maria Victoria traveled 32 miles downstream. Okay. So we're going to have a downstream, and you can see in the same amount of time that would take her to row 17 miles upstream. Okay. So we have a downstream component and we have an upstream component. The amount of time that it takes is going to be the same given the distances are different. If the boat averages 6 miles an hour in still water, what is the rate of the water's current? Okay. And so if you read the question, you can see that the answer that we're looking for is C. What is, the variable that we're going to solve is the current. Okay. Now, what you got to understand when you're in a boat and if you're going upstream against the current, then even though through the water you may be doing, like they said here, 6 miles per hour, but the water is moving against you. So your effective speed is slower because the water is working against you. Anybody that's ever been in a river knows this. Likewise, downstream, the current pushes you faster. So even though you're still going through the water stream at 6 miles per hour, the water is moving also in the same direction. So you are effectively moving faster. Okay. And so what we'll do is we'll go ahead and go into the um, table and fill out the information we know. So let me just kind of drop this down and let me explain where these numbers come from. Okay, so here I've labeled my two components upstream and downstream. Okay, now let me grab my writing tool so I can just annotate some stuff. Okay, so when I read the problem and I've got upstream and downstream, it tells me that 32 miles downstream. So I'm going to put the distance 32 right here in the downstream distance in the same amount of time that it would take her to row 17 miles upstream. So I know the distance here. So that'd be the next thing I put in. If the boat averages 6 miles per hour in still water, so I know the speed of the boat, I'm trying to figure out the current. So upstream, since the current works against me, it's going to be 6 miles per hour minus whatever the current is. That's what I don't know. That's what I'm trying to compute. When I'm going downstream, I'm still moving 6 miles per hour in the water, but the water is moving in the same direction. It is helping me, so I will add the speed of the current. So here's my rate, and my rate includes current, but I don't know the value. So now that's all the information that I've been given. But what did they tell me? And I've got it underlined. They told me that this event, the 32 miles downstream and the 17 miles upstream, takes exactly the same amount of time. In other words, the time up is equal to the time down. Now I have to be able to write an equation, so I have to find something equal to something. So here I know that it's going to be time. Well, time, if I'm trying to compute the time and I know the rate and the distance, I can just simply rewrite the distance formula, D equals RT, and I can solve this for time. So I would just divide both sides by R. So time is actually the distance divided by the rate. So in the slot for the time, I'm going to do that. The distance, 17, divided by the rate, 6 minus C. So that represents, if I know the value of C, how long that would take. Likewise, the time going downstream is distance 32 divided by the rate, 6 plus C. So there's my two times. Now, what can I set equal to each other? I can set time equal to time because they told me that the times are exactly the same. So therefore, I do have an equation that I can write. Again, the objective here is to get an equation written, right? So here I'll go ahead and clear out this box completely. And so here, the 17 over 6 minus C represents the time, right? Going upstream, and that's equal to the 32 over 6 plus C is the time going downstream. They are equal to each other. I have an equation. Notice what kind of an equation it is. It is what? It is a proportion. So to solve for C, I simply do the cross multiplication, which I showed you right here. I'll just put a check there. Okay, and then I'm not going to go through the whole solution. You do your distribution and solve. It's a linear equation. And when you solve it, you get 1.84 miles per hour. Okay, so again, you fill out what you've been given in the chart. What is the variable you're solving for? And you can express rate or time or distance in terms of the other two, depending on what it is that you're trying to solve for. Okay, so you may have to watch that again for it to make complete sense. Here's the next problem, and notice slight variation. Okay, on a float trip, Joel traveled 39 miles downstream, right here, in the same amount of time that it would take him to row 19 miles upstream. So we see that time, once again, is going to be equal to each other. But here, what's different? If the speed of the current is 3 miles per hour, so here they're telling us the current speed, they're asking us to find the speed in still water. So the other one, we found the current. This one, we're going to find the speed of the boat traveling through the water. Okay, so what do? We go ahead and we start filling in the information that we have been given so that we can set up an equation. Okay, so once again, here is the table. What do I know? I know that my distance upstream is what, 19? Okay, so I'll put that in. I know my distance downstream is 39. I know the current is 3. Now, S, that looks like that's not a 5, that's an S. That's the speed in still water. I don't know what it is, so that's my variable. Upstream, the current works against me, so it's going to be my speed minus 3. Downstream, it's working for me, so it'll be my speed in still water plus 3. adding the current. So I know the rate and I know the distance. I can compute the time using the same formula, solving it for t, where I have t is equal to d over r. So I'll go ahead and represent time as the distance divided by the speed. This equation, I can do exactly the same equality because they tell me that the times were exactly the same. So I'll do exactly what I did before. I'll set the two times equal to each other. The upstream equals the downstream time, and then that's a proportion. So I'll do my cross multiplication, and then I go ahead and I solve the equation. And when I do that, I'll get my speed in still water is 8.2 miles per hour. Okay. Okay, this particular problem is going to be a little bit different. Again, this is what math is about. You got to take a look at what you got and then figure out how to solve it. So Gwen was on a 339-mile long road trip. Okay, so this is the total distance driven. It's not up and back. It's in one direction. During the first part of the trip, there was lots of traffic, so she only averaged 23 miles per hour. So there's a rate. Okay, we'll call that for the traffic. The second part of the trip, there was no traffic, so she could drive 54 miles per hour. There is another rate for part two, or the second part of the trip. And then the time, we don't know anything about the time other than she spent 2 hours longer after the traffic cleared than when she was stuck in traffic. So the question that we have to answer, how long did she travel at each speed? So we're going to be solving for t. Okay. So where is our equation? Well, what we do know is that the total distance is 339, and we have enough information to write an equation where we have the distance for part one when she was in traffic added to the distance when she was not in traffic. We know that the total distance is 339. So if I can get distance represented and distance two represented, I can write the equation. Okay, so let's take a look at what we can put into our chart. Okay, what were we given? We were given the rates. So you can see that part one, her rate was 23 miles per hour. On part two, she sped up to 54 miles per hour. The amount of time she spent, we don't know exactly. So I'll call in part one that she spent T hours in traffic. All I do know is that she spent 2 more hours not in traffic. So whatever time she spent in traffic, I have to add two to that answer to determine her time not in traffic. And T is what we're solving for, the time. The total distance, well, distance is equal to rate times time. Since I have values in both rate and time, I can just multiply those. So there's where I get 23 times t, or 23t, and 54 times t plus 2 is 54 parentheses t plus 2. So we agreed that my equation is I can take the distances and add them together, and I know that it equals 339. Well, the distance contains the variable t. So when I solve the equation, I am solving it for t. So let's do that. Let's just write the equation. Okay, so distance one plus distance two is equal to 339. Well, distance one was 23 times t, distance two, 54 times t plus 2. I'm adding those together, and I set it equal to 339. And when I do that and do the distribution, I'm not solving the whole thing. You can do that. I'm going to get an answer of t is equal to 3. So to answer the question, she spent 3 hours in traffic. Why? Because the t in part one represented the time in traffic. She spent 5 hours in no traffic because it was two more than T, which was the time that she spent in traffic. So uh, the 3 plus 2 is equal to 5. And so thus I've answered the question. Fill in the table using the formula, figure out what can you set equal to what, and then just it's always going to be a pretty easy equation to solve. Yeah, now we're going to look at a different type of word problem. These are going to be work problems. And so let me just kind of read this and I'll underline some key points. So you own a print shop and you want to run extra printing press to get the printing done more quickly. So press number one takes 6 hours to do the job by itself. Press two would take 12 hours to do the job by itself, but we're going to have them both work together. And so the question is, how long will it take the printer to get the magazine printed if both presses are running together? So these are going to work together. Okay, so the key thing, and these are pretty easy to understand, is this idea of a rate, right? You use rates all the time, and rates contain different types of units. For example, when you talk about the speed of your car, what do you say? I'm going 60 miles per hour. Well, that's a fraction where the numerator is miles and denominator is hours, different units. So it is a rate. Likewise, miles per gallon, we say MPG, but it's really a fraction. It's miles on top, gallons on the bottom. It's a rate. Okay. In this particular case, it's job per hour. Okay. And so when we write this as a rate, we think of the numerator, and it's always going to be a one because we're talking about to complete one complete job, the rate it would take is 6 hours. The second fraction to complete one job, the rate would be 12 hours. Okay. And so if we write these as fractions, the part of the job complete. So you can see in this chart over here, I've circled it. So we're given the information about the various rates, and together the T is what we don't know. Okay. And so I write the rates as fractions. Complete job in 6 hours, complete job in 12 working together. I will have one complete job in how long? I don't know. T hours. That's what I don't know. But I do know that if I combine the rates together, so here you can kind of see before I show the equation, that if I add the rate of the first press and the rate of the second press together, it will give me the time in the denominator, or the final answer, which the variable's in the denominator, what the combined rate is. Okay, so let me lower this a little bit. So the equation that you write is really pretty simple. My rate for press one is 1/6. Again, one job, 6 hours. Press number two, one job, 12 hours. If I combine those rates together, I will be able to complete one job in T hours. I don't know exactly how long that's going to be, but I can now solve for it given I've been able to write an equation. So what do? We just take a look at this. Well, it's an equation and it has denominators. We want to clear the denominators and solve. And these are usually very, very easy equations. So what is the LCD here? Well, the LCD, I got a 6, a 12, and a T. So 12 would be the number and T is the variable. It's all the unique factors, okay? And so if the LCD is 12T, and I multiplied both sides of the equation by 12Ty to clear out the fractions, then you can see, and let me go ahead and kill this entire, you can see that when I distribute the 12T into each, so imagine I've distributed the 12T and it's multiplying the 1/6. Well, what happens here? The 6 cancels itself. 12 divided by 6 is 2. So 2T times 1 gives me 2T, which is right there. And then if the 12T multiplies the 1/12, the 12s will cancel out, leaving me just T times 1, which is just T. So again, I'm eliminating all the fractions, and then on the right side, I multiply by 12T. The T's cancel each other out, leaving me the 12. 12 times 1 is 12. There's a very, very simple equation that results. And so just combine the t's together and then divide by 3, you get an answer of 4. Okay, so you take a look at your rates of work, add them together, and for one complete job over the time, you can compute the time it takes to work together. Okay, so let's take a look at another one. Okay, so Fred can mow the lawn in 30 minutes. Melissa can mow the same lawn in 60 minutes. How long does it take Fred and Melissa to mow the lawn if they're working together? Feel free to stop and work this on your own. I'm just going to go ahead and continue. So my basic table, you almost don't need a table for these. I crossed out the hours. These are minutes. So 30 minutes for Fred, 60 minutes for Melissa to do the complete job. So therefore, the rate that Fred works, he can complete one job in 30 minutes, so 1 over 30. Melissa, one job in 60 minutes. If I add their rates together, then I'll have one complete job done in T minutes. Okay, so there's what I got to figure out, the T. How long did it take? So again, this is a very simple equation. I'll just kill it. My lowest common denominator is 60T. Here I explicitly show every term being multiplied by 60T. So that's in green, the original equation. 1 over 30 plus 1 over 60 equals 1 over T is in red. And you can see that when I cross out all the common factors with the denominators, the 60T times 1 over 30, 30 cancels with 60 to give me a 2. So that's where the 2T comes from right here. Then the 60s cancel each other out, leaving me just a T. T times 1 is a T, so there it is there. And then I canceled the T's on the other side, leaving me just 60. 60 times 1 is 60. And then boom, 2T plus T is 3T is equal to 60. Divide by 3, you get 20 minutes. Okay, the next problem, just slight little variation. Again, they're not all going to be exactly the same. This particular problem, they tell you that John Mark can shovel the driveway in 6 hours, so there we have a rate. But if his brother Kyrie helps, it would take 5 hours. Now that's 5 hours total. That is not Kyrie's rate. That is the rate if they work together. Okay. And so the question is, how long would it take Kyrie to shovel the driveway alone? So what we don't know is the rate that Kyrie can do it by himself. So if we take a look at the table that we've been setting up, the only thing that changes is the unknown, where the variable is, where the T is, right? So if John can do the job in 6 hours right here, we don't know how quickly Kyrie can do it. That's what we're solving. But we do know that the rate, the part of the job completed per hour by John is 1 over 6. Well, therefore, the part of the job done by Kyrie, we don't know. It's going to be one job in T hours. We're trying to compute that, but we know if they work together that it will be done in 5 hours. So instead of a variable here in the denominator, we have the actual time that it would take combined. Okay, so slightly different. Instead of the variable being on the other side of the equal sign, it is one of the rates of work we're trying to compute. Okay, so same kind of process here. The lowest common denominator was going to be 30T. If I multiply everything by 30T, so the 30T's in blue, the original equation is in green. If I do all the cancellations by now, I would hope it's very obvious what's going on. I quickly get 5T plus 30 is equal to 6T, and just by subtracting 5T from both sides, I get T is equal to 30. Okay, so not difficult. Once you got the idea, these are very simple. This one again, it's just a slight variation, but one that should make sense. If you read the description, one inlet pipe can fill an empty pool in 8 hours. Okay, so it's filling up a pool, and we got a rate. And a drain can empty the pool in 12 hours. Well, we have a rate, but it isn't filling the pool. It is draining the pool. So it's working against the other rate. How long will it take the pipe to fill the pool if the drain is left open? Okay, so if you read this, I think you understand that water is going into the pool. Water is also going out of the pool. The water going in the pool is has a higher volume than the water leaving the pool, so it will eventually fill up. But the relationship is such that instead of adding their rates together, we got to subtract the rates because they're working against each other. Okay, so I think that should make sense to you. Okay, so I'll just kill this right here. So if you fill in your little table and write the equation, we can see again the number of hours to complete the job. It can fill it in 8. It can drain it in 12. That means the rates, the part of the job completed per hour to fill it is 1 over 8, one full pool in 8 hours. And the drain is I can drain one full pool to empty in 12 hours. Okay. And so what's the equation? Well, I'm going to fill the pool right here. That's my rate, but I'm going to subtract from that the rate that it's losing water. So the rate of one, it can drain one pool in 12 hours is working against it. So it's subtraction. And the question is, when is the pool going to be filled? Well, I'll have the one full pool will be in T hours. So I don't know how long it will take if they're working against each other. So the only variation here is the subtraction because it is draining and not helping. Same process, my lowest common denominator is going to be 24T. You can see that in green. My original equation in red, the 1/8 minus 1/12 equals 1 over T. Do your cancellations. You quickly end up with a very simple equation to solve. So it solves it, and the pool will ultimately be filled in 24 hours. Okay, I'm going to stop this video here. Covered a lot, and I'll do the last part of this section in a separate video.